In this lesson, we'll look at the chain rule a little bit more in detail, and we'll also look at the derivatives of exponential functions, and this will include a small review of what exponential functions are. So just to start with, here's a little more official way to look at the chain rule in our little problem here. Find the derivative of y equals the quantity 3x plus 4 to the fourth. And so what we do is we say, well, this little thing in here, 3x plus 4, it kind of reminds us of y equals x to the fourth. And if you had y equals x to the fourth, you could just use the chain rule and get the derivative with 4x to the 4 minus 1, 4x cubed. Except instead of x, we have 3x plus 4. So what we do is we call that 3x plus 4 a u. That's the thing that we're kind of substituting there. And so then if you took the derivative, we know how to take the derivative of 3x plus 4. It's a line with slope 3, mx plus b. So say the derivative of u with respect to x, right, because it's got an x in there, is 3. And then similarly, from that, we can substitute the u back in the original equation. So where there was 3x plus 4, we put the u. And then it's to the fourth power, so u to the fourth is another way to write that. And now, this says find the derivative of f or the derivative of y with respect to u. And so we treat the u like an x, so we can use the chain rule for u to the third. And we use a little trick here. If you look at this, if you want to take the derivative of f or y with respect to x, you can take it with an intermediate value du, and then take the derivative of du dx, multiply those two times each other. So when you take the df with respect to u, that was this 4u cubed, and then times, and then the du dx, that was the derivative of the 3u with respect to x, so that was the 3. And then the 3 and the 4 can be multiplied together, 12u cubed, and then we unsubstitute 12u, remember, is another way to write 3x plus 4. That's the secret or the trick of the chain rule. That may not be the easiest way to think of it. Most books show it this way, that I just gave you the 4 steps. But you might just think of it like, hey, it looks like x to the fourth, so do kind of what you want, like 4, I think we said just take it, just say, look, you kind of want to make it 4 times 3x plus 4 to the third. And then just remember that's not x, so you have to pay a penalty, which is the derivative of what's inside, which would be the 3. So that's the quick way. All right, so then the derivative of e to the x, this is one that you just have to remember. The derivative of e to the x is itself. It's the one function that its derivative is the same. It's not y to the first, it's y prime, or y with an apostrophe. The derivative is the same as the original function. Now this here, this is a little bit different. In this case, we have, we kind of want to say, well, it's e to the power, so we kind of want to say e to the 4x minus 1. But then we have to pay a penalty. This is called the chain rule. You kind of do what you want, but then you have to pay a penalty. And the penalty is you have to take the derivative of, respect to x, of 4x minus 1, or what I call the trash all the time. It should just be 4. So it's times 4. And an easier way to write that is 4e to the 4x minus 1. All that in the exponent up there. Now here's another one. We could say, that is, let's write that. Whenever you see something in a square root, it's probably best to go ahead and write it to the 1/2 power, just so that you can see that power rule if you need it. Now you see we really want the power rule here. You really kind of want to say, don't you, for the derivative, that it's 1/2 times 5x plus 1 to the 1/2 minus 1. That's the power rule. But the power rule only works for x to the power, right? So if y equals x to the n, then it's y prime is nx to the n minus 1. But we didn't just have x in there. We had this more complicated thing. So the chain rule says you have to take the derivative of the complicated thing. In this case, it's just a line, so the derivative is 5. And we're done. So 5 times 1/2 is 5/2. And then 5x plus 1, and then 1/2 minus 1 is minus 1/2. That's a pretty good answer there. I like it. Some students like to go ahead and put it back in the form like it was given to us. And then some students have been trained to do it what we call a no radicals in the denominator kind of thing. Anyway, I'm not going to go any further, but the boxed answer is what I'm kind of looking for you to get to at this point. Okay, so let's try a little problem here. Let's find the marginal revenue function for the demand function given by this thing. And now this is a little bit more complicated. And this is also not the revenue function. We want marginal revenue, so we want R prime. And this is P. So for R, remember R is Q times P. And that's the same as Q times, in this case, P is 40 over ln of Q plus 3. It's natural log. So I'm going to put the Q on the top, 40Q over natural log of Q plus 3. So there's our revenue function. And we want the derivative of that guy. So you can see that we can take the derivative of the top. We know what that is. If that was an x, it would be 40. And the bottom might be a little suspicious, but we might just think about that for a second. If you have natural log of x, we said there were two you have to memorize. If you have e to the x, the derivative of that is e to the x. And if you have natural log of x, the derivative of that is 1 over x. So you might say, well, what about natural log of x plus 2? And then we say, well, you want to do 1 over x plus 2, right? Because natural log is something, the derivative is 1 over that something. The thing is, it's not just x, so we have to use the chain rule. Because it's a little more complicated expression. Well, what is the derivative of this guy? It's pretty sweet, because the derivative of this line, 1x plus 2, is just the slope of the line, which is 1. So it's just 1. So we got away with 1 there, didn't we? 1 over x 2. So if I said, what's the derivative of ln of x plus 10, you would say, oh, that's the derivative of that guy is 1 over x plus 10. So in here, we can take the natural log of q plus 3 pretty easily. So this is a u over v situation. So we'll use the quotient rule. And that's r prime is u prime v minus uv prime over v squared. How do I remember which one's first in the minus? It's alphabetical order, uv, right? QRST UV, it's in alphabetical order. So we need a u and a v and a u prime and a v prime to plug into that guy. And the u is the top, 40q. And the v is the bottom, natural log of q plus 3. Pretty awful, right? Except the derivative of this is just 40. And the derivative of natural log of that is just 1 over q plus 3, right? And then the chain rule, but the slope of the line is 1, so we don't have to worry about anything. Then we just plug those in. So u prime is 40. V is natural log of q plus 3. I didn't say it would be a pretty expression. Minus 40q times v prime, which is 1 over q plus 3. All over v squared, so natural log of q plus 3 squared. And I'm done with that one. We can play with that if we want some other time. All right, so let's look at some derivatives of exponential functions. And to really get into it, let's just review why you might use e for a financial application. So e to the x, remember simple interest. You've got principal, rate, and time. And if you want to borrow $100 at 6% for 5 years, simple interest. In year 1, you'd have your $100, and at the end of the year, you'd get your 6% of your $100. And at year 2, you'd have your $100 plus your first year 1 money, and then you'd get another 6% or $6. And so that's just how it works. In the third year, you'd have your year 2 money plus your third. And that's this little formula for simple interest. One example of simple interest that I usually use is treasury notes. Now, compound interest is a little different. If you're compounded once per year, you'd have the same as the simple interest in this case. But for the second year, there's our first year money. But we'd also have interest on the interest, right? This is different than this. This is just interest on the principal every time. This is interest on the interest, so it's compounding. And so you can see there's a little exponential thing happening here. And then if you fiddle with that exponential thing with some algebra, you end up with this little formula. And as n, the number of compounds per year, you might have 1 for an annual interest. Annual compounded interest, you might have 12 for monthly compounded interest. You might have 365 for daily compounded interest. And if you go more and more, like instead of just days, every hour, every minute, every second, and then infinitely small pieces of time, you have this limit. And if you plug in some stuff into this, and we do this in 1324, and you calculate it, and for any r, and for any t really, you can just take those out basically, just make them both 1 or something, then you'll end up with the definition of E, this right here. This converges to 2.718, some more digits. And this is a little formula you'll see for continuous interest. And there is a question, is there a function that it's its own derivative? And the answer is yes. There is one unique function that's its own derivative, and that's this e to the x. So if you want to play with this, I'll let you look at this on your own time, but basically you can just go through and figure this out. I gave you enough detail there, you can see the proof. So I've just been saying, just memorize that, if you have y equals e to the x, then y prime equals the same thing. Or I also like to write this sometimes. I'll write e to the x, if you take the derivative, you'll get e to the x back. And the other one I gave you was if you have natural log of x and you take the derivative, that's what this little d is on the arrow, then you get 1 over x. And then for any other base, though, if you have a to the x, so let's say you had y equals 10 to the x power, that's an exponential function with a base of 10, then the derivative of that would be kind of what you want, 10 to the x, right? Just like e to the x is its own derivative, but it's not e, so we have to do a little natural log of the base, so natural log of 10 times. So let's try it. If you find the derivative, y equals e to the x, y prime is, you already memorized that one, e to the x. Y equals 3 e to the x. So remember this little guy. We have a constant, 3, times a function, so we just do them separately. Pull the constant down, don't take the derivative, just say, all right, it's 3. And the derivative of e to the x is e to the x. What? Yeah, it's the same thing. And then 2 to the x, that's not e, so we want to say it's the same, 2 to the x, but it's not e, so we have to pay the price, and that's times natural log of 2. And then at 3 to the x, you might think on that for a moment. That's what you want to do, but it's not e. And then this one here, if you have this guy here and you want to take the derivative, what you want to do with e to the x is write the same thing, right? E to the 2x plus 1, because it looks a lot like e to the x. But we really have kind of a u here. See the substitution you could do to make it e to the u? And that means it's a chain rule. So we do what we want, and then we take the derivative of the trash. And the derivative of 2x plus 1 is just 2. So we really just have 2e to the 2x plus 1. And you can do all that dx, du stuff if you like. Here's, if you don't like thinking of the e to the x the way I talked about with the trash, you can use this chain rule. You can see I just did. In this example up there, I said let u equal 2x plus 1. Then we had y equals e to the u. And so we can say the y prime is e to the u, so e to the u, times du dx. Well, du dx. If u is this, the derivative of this with respect to x is just 2, so times 2. So 2e to the u, and that's 2e to the unsubstitute, 2x plus 1. Seems like a longer way than what we talked about here to me, but whichever way works for you, this is the formal way on the bottom. Okay, so one it's a little more interesting. Here's one where it's got two things involved. So this is a constant times a function, so the constant we'll just pull down, times. And then the function is e to something, so let's just write that, e to the 4x squared. But it wasn't just x, so then the chain rule says, take care of your trash. What's the derivative of 4x squared with respect to x? Take the derivative of that guy. We get, 2 times 4 is 8, x, and then x, 2 minus 1, once, just 8x. So we have 13 times 8 is 104x, right? There's an x there. E to the 4x squared. So you might have to do a few more, and you can look in the homework problems for that. All right, so let's try one application problem here. So a continuous growth problem here with a pretty high growth rate, 30%. Given the equation y equals 50, I'm sorry, that's a equals 50 e to the 0.3t. So the a was removed there. 0.3t, which models continuous growth, find the following. The derivative of a with respect to t. So let's take the derivative of this guy, except that instead of with respect to x, we're doing t's now. So it's all right. So a dAt, we write that as a prime often, is, all right, so it's a constant, 50 times a function. So constant times, just pull the constant down. And then e to a power, we just write the e to the power. But that's not just t. If it was just t, we'd be done, but it's not. So then we have a chain rule issue here. So the derivative of 0.3t, we call that u sometimes. Or sometimes you'll see me just write u prime, would be, or dt, sorry, would be just 0.3, because that's a line with slope 3, right? 0.3t plus 1, so 0.3. So 3/10 times 50, 15 e to the 0.3t. So we can find the derivative pretty easily. Now we say, what's the rate of growth at time t equals 2? Well, this is a rate of growth, right? A prime, the change of amount with respect to time. It's a growth velocity, so it's a rate, growth rate. So what is the rate of growth at time t equals 2? We just plug in, we want a prime of 2. So a prime was 15 e to the 0.3 and then 2. So 15 e to the 0.6. We need to do e to the 0.6 power on the calculator. Which is 1.822. And I'm just going to leave it all in the calculator and multiply times 15. We get 27.33 or 27.3. In general, if all your numbers have no decimal points, like 50 and 2, then you give it 1 decimal point. You always give like 1 more decimal point of accuracy in your answer, just to help for intermediate stuff. So what's the derivative of this thing? Y equals 3 to the 2x squared. That's a little weird one. So you say, all right, y prime equals. Say, that's not times, it's a exponential function with base 3. So we want to write it's 3 to the 2x squared. But the problem is this is not base e, so we need to do that little natural log of 3 on the front, like by that rule on the last page. And also, it's not 3 to the x, so we need a chain rule on the back side of that thing. 2x squared. If we take the derivative of that, we get 2 times 2 is 4. X to the 2 minus 1 is 1, so 4x. That's just awful, so I'm just going to box it like that. You can try to make it prettier if you want, but there's no combining you can do to make it more interesting. All right, that's the end of the lesson.